Hello there. In the last video, we worked on how to solve first-order differential equations using a forward finite difference approximation method, which is pretty much encapsulated in this line here. And we were able to solve the differential equation sine t over t plus y+1 plus e to the minus t squared with initial conditions y of 0 is equal to 0.3, where this function can pretty much be any function of t and y as long as the initial condition works out in an appropriate manner. So in this video, what we're going to do is pretty much build on top of this code to sort of discuss how we can solve a coupled system of first order differential equations. So we're going to have two equations, y prime of t is equal to f of ty, and say z prime of t is equal to g of ty, and also these functions can be functions of the other function. So y can be a function of z, or y can change as z changes, and z can change as y change. So we're going to pretty much work through that extension in this video. Alright, so let's begin by creating another function that we want to solve here. So we're going to be solving, let's call this now a prime of t is equal to f of ta. So we're going to solve systems of the form a prime of t is equal to f of ta. And we're also going to have b prime of t is equal to g of t b. And we'll also include b in the first equation and a in the first equation eventually, but we'll keep it simple before we move on to that. Alright, so g is going to be equal to a function of t and what are we going to call it? Let's call it b. So let's keep it consistent. So that's going to be a. So I'm going to change this y to a, so that's a function of t. And let's make this sine of t dot division t plus b plus 1. So same function, just different direction. Plus the xb minus t squared. And let's add another term to this just to make it a little bit more exciting. Actually, no, let's keep it there. So we can test to see that it's solving in the right ways. Because we already know what this solution looks like. So we're going to know what that solution looks like to sort of check our code. We're going to have the same exact initial conditions, so let's change up this comment. So we're going to have a of t0 is equal to a0, and we're going to have the initial condition for b as well. So where's my percent key? There it is. So we're going to have b of t0 is equal to b of 0. So ideally, these two functions are going to start at the same exact time, but may have different values. So a0 is going to be that, and b0 can be something else as well. Let's call it 0.8, so it starts off a little bit higher. H is going to be the same, t final is also going to be the same. Alright, so let's change this to a old is equal to a0. We're also going to include another term, b old is equal to b0. So now we're going to be plotting two different solutions on the same exact grid. So in a figure, what we can do is create what we call subplots. So subplot 1 comma 2 comma 1. So this is a 1 row by 2 column matrix, and in the first cell, going from left to right, top to bottom, is where the first thing is going to be plotted within. So 1 row, 2 columns, first cell of that array, this is going to be plotted there. So that's going to be a old. And in the same array, in the same figure, again, it's a 1 row by 2 column matrix. In the second cell, we're going to plot t current comma b old. We'll do this in a different color, say red. Alright, so if we were to run this code, it should show us the initial condition for both A and B when t is equal to 0. All right, so this t current is not going to change, so I'll just keep that there. We're going to have two separate solution equations here. We're going to have for variable equation 1, so this is going to be A, and then we're going to have the same for variable equation B. So let's change this up a bit. So this is going to be A new is equal to A old plus H times F, t current minus H times A old. Then we're going to plot A new there in blue, and then A old is equal to A new. We're going to do the same exact thing for equation B. So this is going to be B new is equal to B old. So this is now evaluated at function G because G is associated to B. It's going to be B old, and then we're going to plot B new there, and then B old is equal to B new. Same exact limits on my curve. Now remember, we need to be plotting these things in the appropriate subplots as well. So before we have this plot command, we're going to put subplot 1 to 1, same array values, and then here we're going to have subplot 1 to 2 for that particular plot. Is that it? I believe so. Alright, so let's just make sure we have everything going on here. So we're plugging in values of B into G in the second parameter and plugging in A values in the second parameter of F. So let's look at this. So this is a T value, A value, T value, B value. So these values are not coupled, so I can actually, if I want, do like a threading type of thing and do like a parallel computing style approach. I can run this in a for loop on one thread and run this in a for loop on another thread in parallel. So it actually cuts down the computation time by a half. But we're eventually going to couple these where you need actually the solution at t is equal to a to calculate the solution for t is equal to a plus h for both f and g simultaneously. So let's give this a run through. So let's see what happens here. All right, so, okay, yeah, we don't want this. Notice I didn't change the colors, so this should actually be red like this first point, but we can change that in the next run through if we want. We're also going to include the grids as well once we get through. And if we want to actually watch this continue, we can, but I'm not going to go through the things. Also, if you're not familiar with, you can go into this and do Control C, and that's going to terminate the current code. All right, so let's just make that little change. Let's also throw the grid on for that comment. So grid on. And now it should be graphing. Okay, now we're on a grid and now it's doing the appropriate colors. Wonderful. All right, so now what I want to do is I want to couple these equations together. So usually we call this like the temporal portion, the temporal portion of the differential equation, where it only depends on time, and also the other equation. And then there's also this dependence term. So we can call these the dependent functions. So f is going to be the function in f whose dependence is the other variable, which in this case is going to be b. So I'm going to define that function to be equal to 0 initially, and g is going to be the portion of little g such that it is dependent on the other variable, which in this case is going to be a, which I'm going to define to be 0. So I'm going to define this to be f of, what is it going to be? F of b. We're going to add it to that term. And then we're going to have f of a, and we're going to add it to that term. That should be actually g. So if I were to run this code, nothing should change. But keep a note here that now f is a function of a, t, and b. So I need to add this into this argument term, and I need to add a here as well. So since I'm changing the definition here, how I implement this in my code also needs to change. So here's my f value. So we're going to start with a t value, an a value, and also the b old value. and then we're going to use t values, so a value and comma b value. So these things have to be consistent throughout the entire code. So since f and g are both defined to be equal to 0, they're actually still uncoupled equations, because since these are both 0, these terms right here are actually non-existent. It's when I make these terms non-zeros where these things get fun. So if I graph these two curves as time goes to 20, the solution should be remaining the same. To make it a little bit more interesting, now I'm going to create a coupling term. So what I can do is sort of have an interaction term that's a function of both variables, say a and b. Since I have that flexibility now, so I'm going to add a sign of a times b there, times a sign of t. So now it becomes a little bit more interesting. So now this function is going to be a little bit more different. And it's actually going to behave in a completely different way. And if I want to make things a little bit more interesting, I can make these terms f of b and f of a. The terms that only depend on a and b, I can also introduce them as well if I want to. So this now is a coupled equation, so I can introduce terms if I want here. So I can make this like 1 divided by b plus 1 dot division, just in case I want to do some vector stuff. And for this, I can make this, say, an e to the minus, so exp minus a squared term there. So this is actually here, and there's reasons for which you may want to do it on separate lines, just in case you may want to have these as flexible terms if you want. So let's graph these solutions as t goes to 20 and see what happens. So it looks like the function a wants to go to infinity, but b tends to, be increasing, and now it tends to want to go up. So we can watch this solution evolve as time goes to 20 if we want. But while that sort of goes through its simulations, we can sort of just review what we've done so far. So we have some function f, some function g that's now a function of both time and the variables in the system. So it's a two-dimensional system that's a function of time, which could have a variety of applications. Our time step is equal to 0.01. If we want to make this a little bit more accurate, you make this a little bit slower, but it's actually going to go through the simulation slower. And if this is not small enough, it's possible that this is actually not the actual correct solution to this system of differential equations. So you need to keep that in mind. So sometimes you may want to try a smaller h and do it for some small time just to make sure it's the same solution on some short interval of time, just to give you an idea of actually if it's the correct solution as time goes to whatever t final is. So let's see what's going on here. Let's fast forward this and see what happens as t goes to 20. Alright, so now we've solved our equation through our t final, and we have this interesting solution where it sort of is increasing, and does this weird little shape in the middle. But we have this nice sinusoidal increasing function for the function b, which actually looks pretty nice. But you can model definitely a lot of different types of phenomena with this type of stuff. So the possibilities that you can solve in terms of equations of this structure is extremely broad. But this is just some foundations on how to solve a coupled system of first order differential equations. You can definitely add as many equations here as you want, even add some more variables if you please. The process would be exactly the same. The only thing that will make this a little bit more complex is if you want to add, say, a spatial term for this. For example, we're studying variables A and B, so this could be pressure and this could be temperature with respect to time, but it also could be a function of space as well. So you could add X, Y, Z, or other spatial dimensions if that would be your interest. But this is just some groundwork for systems of differential equations of single variables, not partial differential equations. But we will get to that eventually. But at least this gives you some idea of how to start the code. Hope you enjoyed.